Hello, everyone, and welcome to the CrySP speaker series on privacy today. And today we have a speaker, Yibin Yang from Georgia Tech. So Yibin is a fifth-year PhD student, and he works in applied cryptography, zero-knowledge proofs, and multi-party computations. And today he's going to tell us how to build a ZK CPUs. So without further ado, let's welcome Yibin, and the stage is yours.
Okay. Yes, thanks, man, for this very nice introduction. So it's very happy to be here today. So I'm Yibin Yang, currently a fifth-year PhD student from Georgia Institute of Technologies, working with Professor Vladimir Kolesnikov. So my research is mainly about cryptography, and it's with special focus in zero-knowledge proof and secure multi-party computations. So today I'm going to talk about one of my major research line of work during my PhD study, which is named as this zero-knowledge proof beyond circuit and constraints. So, and I'm pretty sure by just seeing this title, you don't really know what I'm going to say about, but you're going to see as it goes. Okay, but basically what I'm going to show you today is that how you can efficiently emulate some kind of the CPU machine learning inside the zero-knowledge proof systems. Okay, so let's get into it. So I guess we have a very broad audience here. So let me first introduce what is a zero-knowledge proofs. So zero-knowledge proof is a cryptography protocols where we consider two parties, where one is the proofer, the Alice, and the verifier, the Bob. And in particular here, the proofer just want to prove to the verifier that some statement is true without leaking anything beyond that. So as a specific examples, here is the Sudoku puzzles. Here, the proofer Alice and Bob know this Sudoku puzzle, which is the zero-knowledge statement. And in particular, the proofer know the solution of these Sudoku puzzles. Okay, and here the proofer, the Alice, just want to convince Bob that she knows the solutions. So the zero-knowledge proof allows these two parties to interact with each other, talking back and forth. And finally, the Bob will just output a Boolean value to indicate whether the Bob believes this statement or not. And in particular, in zero-knowledge proof, we want the following three properties. The first one is called the completeness. It means that if Alice here actually knows the solution for these Sudoku puzzles, the Bob should output true. The second one is called the soundness. It means that the malicious proofer, if Alice does not know the solution for these Sudoku puzzles, no matter what Alice is trying to do, the Bob should output false with large enough probabilities. The third one is called zero knowledge, which may be the most fascinating property here, is that after these interactions, the Bob should learn nothing beyond the fact that the Alice knows the solutions of these puzzles. Okay, so of course, in the real world, we want zero knowledge proof beyond just the Sudoku puzzles. Okay, in particular, we want some zero knowledge proof that can work for generic statements. So one very popular way to define this is that the proofer and the verifier are going to describe their statement using a circuit. So here is the circuit defined over some arbitrary field you like, and with some gates, addition and multiplication gates. And in particular here, proofer just want to prove to the verifier that she knows some input to the circuits that can make this circuit output to zero. This is called zero knowledge proof for circuits. So, for today's talk and for you guys, before we go beyond the circuit and constraint, I just want to spend a few minutes to go over how people usually do for the circuits, zero knowledge proof. And you will better see what do I mean when we go beyond the circuit and constraint. So with, in particular, I'm going to introduce you very briefly how people do zero knowledge for a circuit using a paradigm called commit and prove paradigm. So to introduce this paradigm, I need to go over a cryptography primitive called the commitment scheme. So in particular here, I'm going to define the commitment scheme for a large enough field. Field means that it's just some simple poly in the security parameters. So here the proofer knows some value X inside these fields. So the crypto commitment scheme is such an algorithm which allows proofer to generate this bracket of X. Here in this talk, I'm going to use this bracket parenthesis to denote that this X is commit by Alice. And you just put this inside this box and send to Bob. In particular here, the Bob, seeing this box, should know nothing about what is committed by Alice. This is called the hiding property, meaning that the Bob doesn't know what is committed by Alice. Later on, the Alice may want to just open this X to Bob, saying that Bob, what I just put in box is X. And in particular, the cryptography commitment require us to have some binding property, meaning that a malicious Alice here, the proofer here, should not open this box what put X inside to other any value besides X. And I'm going to assume like this commitment scheme also have some property called linear homomorphism. In particular, this means that if Alice and Bob holding this commitment, this box of X and the box of Y, and there are also no three constants, the three public constant ABC in this field, Bob, without communicate with Alice, can also construct a box which inside should be AX plus BY plus C. Okay, so I'm going to show you by using this cryptography commitment how you can design a zero-knowledge proof using this commit and proof paradigm to prove the zero-knowledge proof for this circuit. In particular, the Alice, the proofer, knows some input that can evaluate this circuit to zero. So how it looks like. So here, the proofer just going to commit the input of the circuits and going to commit the output of each multiplication gate. Okay, and by utilize this linear homomorphism, you just see the two parties can just locally calculate the commitment, this box on each left wire and right wire of multiplication gates. Also the output of the circuits, because I already commit everything related to multiplication gates. So what's left is just some linear operations. And finally, what proofer need to show to the verifier is just this, whatever proofer commit in the input evaluated to zero. This means that the output is zero. You just open the box and it's zero in size. And of course, you need to properly prove that the multiplication gates are formed correctly. It means that for each multiplication gate, there's some left wire input, right wire input, and it's going to be the output. You need to design some customized zero-knowledge proof system to just show that the left wire and the right wire you element-wise product it, you give you the output here. So of course, I'm not going to say how you're going to prove this and what kind of commitment seeking you're going to use. But what the things I want to convey here is that if you see what's happening here, the cost for this proof is proportional to the circuit size. You give me the circuits, the proof of computation, the verified computation, also the communication is somewhat related to how large the circuit is. Okay, as a particular examples, for example, when you instantiate this commitment scheme using something called volley-based zero-knowledges, which is one of the very popular research line of work now in zero-knowledge community, the computation, the proofer, and the verifier need to pay would be order C, linear in the circuit size, and the communication complexity is order of the circuit size. Cool. So now, it seems very good. So now I'm going to say what we're going to do beyond this circuit and constraint. But if you think about this just for seconds, it's okay, it seems dumb. We can do zero-knowledge proof for circuits. Then because circuit is a universal computation machinery, we can do zero-knowledge proof for like arbitrary statement, NP statement. And it's quite efficient. It's just linear in the circuit size. What's the point? Why we want to go beyond the circuit and constraint? So the things here is that as a modern programmer, we are not going to write our program using a circuits, right? Think about you are working in for a big company, you know nothing about crypto. How are you going to write your statement as a circuits? So what really programmers do nowadays is that they're going to write their program using these languages, right? These are very popular C languages. So it would be very nice if we can design some zero-knowledge proof scheme that instead of working for circuits model, we can allow these two parties to express their statement using a C program. And in particular here, proofer just want to prove to the verifier that she knows some input that make this C program output zero. Okay. Well, we know that you can do this. What we really need to do is that we need to design some zero-knowledge CPU circuits. This is just some circuits inside zero-knowledge which can read this program directly without people just compiling this program into a circuit. So that's the main focus of today's topic. However, this is not trivial. If you think about it, if you want to compile just a CPU machine learning inside to a circuit, it's very challenging, especially in the efficiency metrics. Let me show you why. So that's because in this CPU machinery, we will have some branchings. As a CPU, think about what physical CPU do. You have a bunch of different instructions. Each step, you just execute one out of it. Right? In zero-knowledge languages, because verifier doesn't know which instruction is going to be executed, so we need to properly design this branching mechanism to ensure that the verifier can have a very good efficiency. And the second part is that the CPU need to read and write a very large memory. Notice that the verifier in the zero knowledge proof doesn't know which unit going to be read. So we need to properly design such a machinery to allow the verifier, especially the verifier, to read the RAM efficiently. Okay, and basically we also need to ensure that this compilation preserves soundness. The proofer cannot cheat in this process. So also to just emphasize what I'm trying to argue, so here you can imagine that instead of you have a C program, you compile it into a assembly code. So assembly code is just composed of some basic block. So here the proofer just show to the verifier they agree on this public agreed assembly code. And the proofer just show to the verifier that per step, I'm going to execute one out of these 5 basic blocks. You don't know which block I execute. And finally, this basic block can have a RAM access. Okay, but before we move forward, I just want to emphasize that actually, I also have some other words, even I'm not going to see this in today's talk. But basically, we already show that you can use, you can build a very efficient zero noise CPU in the instruction level, not in this basic block level. And you have some parallelism that can speed up. Also, this kind of way to perform zero knowledge proof can also be applied in the context of two-party computations where you need to design some double circuit primitives that can efficiently support branching and memory. Just feel free to ask me questions, okay, if you want to know what's happening in these papers. So, but what's covered in this paper, in this talk is the following 2 papers. So in the first half of this talk, I will talk about how you're going to tackle these challenges of ZK branchings. The paper is on CCS last year. It's called Batchman, robbing batch and non-batch branching for interactive zero knowledges. So this is joint work with David Heath, Carmit Hazay, Vladimir Kolesnikov, and Muthuraman Krishnan Venkatasubrahmanyam. Okay, and in the second part of this talk, I'm going to show how you can efficiently enable this zero knowledge RAM machinery, which is a paper going to be present in this year Usenix Security, which is called a two-shuffle make a RAM improve constant overhead zero knowledge RAM. And this is joint work with David Heath. And I want to say that before we move forward, I just want to say that if you see that this is just one paper to targeting branching, and this is a paper targeting memory, but they can compose together trivially to achieve a full-fledged ZK CPU machinery. Also, actually, there is some ongoing work where we show that you can actually shuffle these Batchman protocols, not trivially, not straightforwardly, to achieve even a better efficiency in the ZK CPU world. But this is under submission and will be on ePrint soon. Okay, so let's go into our first papers, which is targeting this ZK branchings problem. So what is the problem statement here? We want to prove some ZK disjunctions for the circuits. What do I mean here is that you can imagine instead of Alice and Bob agree on one single circuit, the Alice and Bob agree on B different circuits. Okay, Alice and Bob just say, here's the B different circuit. For example, here you have 3 circuits, and Alice just say, hey, Bob, I know one input of one out of these 3 circuits to make it output 0, but I don't going to show you which one I pick. So here, through this talk, I'm going to, without loss of generality, assume these 3 circuits just of the same size. And you will see why we have these assumptions for a second. But well, what about we just compile this trivially to a circuit? Notice that the verifier should not know which circuit is being proven. So naively handling, what you're going to do is you just copy and paste these 3 circuits, and you have a very large circuit. You have a multipack of these 3 circuits. And well, you can do that. This fits from feasible point standpoint, you can do that. However, I'm claiming that by doing so, you will have a factor B blow up. Well, because you have a larger circuit, you have 3x. For example, in this particular examples, you directly have a 3x overhead. Okay, so we're going to do it better. But before we move forward, I just want to say that this paper also targeting these settings where we call batch disjunctions. Well, what's happening in batch disjunction is just we just copy and paste this single statement multiple times. Right? So in the single disjunction settings, the proofer want to show that she knows some inputs, satisfied one out of these 3 circuits. In this batch disjunction circuits settings, the proofer going to show the same statement but multiple times. Again, you can compile it very down to a circuit, but this will result in another factor R blow up. For example, here I just copy and paste this 3 times. So in total, you're going to pay 9x compared to a single circuit. Cool. So why caring about these batch disjunctions? So just let me remind you, in our applications where we're going to enable this zero-knowledge proof for this assembly code. And what you're going to see is that you're going to, at each step, you're going to execute one out of these 5 basic blocks, right? In batch setting, you just copy and paste. You execute 5 steps. Per step, you're going to execute 1 basic block. So that's why we also consider this batch settings. So before I move forward, I just want to see whether you have any questions so far for what we're going to see next. Okay, so let's move forward. So yes, so what we achieved in these papers is we designed some protocol called Batchman and Robin, where all you need is just some commit and proof hybrid word. But here I'm going to show you our result when we instantiate our protocol using this volley-based zero knowledges. And remember that if you just copy and paste this circuit B time and R times, your computation, communication, and verifier computations will both be order R times B times C. Okay, it means that you're going to copy this same circuit of C size B times, and you copy it R repetitions. So in our first protocol, Robin, we're targeting to optimize this single disjunction settings, where you only have single disjunction you need to prove. Of course, you can still copy this statement R times to finish R proof. But when you apply it here, we basically improve the communication from order RBC to order RB plus RC. We shave a factor there for communications. We further improve the computation complexity in our Batchman protocols, where we show that if we are targeting these batch settings, not only we can improve the communications, we can also improve the proof of computation and the verifier computation from order RBC to order RB plus RC plus BC. This is somewhat surprising, but what I'm going to say is not very it's informal. And what I'm trying to argue here is that if you view this Batchman complexity, the computation and the communications are all sublinear in the circuit size. The sublinear in order R times B times.
Can you remind us what was R and B?
Oh yeah, sure.
I missed it from the previous.
So B is the number of branches and R is the number of repetitions.
Okay.
So you're going to have R repetitions and per R steps, and per step you're going to prove a B circuits, and each circuit is of their C, and you prove the disjunction statement over these B circuits.
Mm.
Okay. Yes. So why are we able to do this improvement? I just want to say that before I move forward, just think about this. That what you're going to see is how this party can reusing resources, and you will see what do actually. But just keep in mind, you're going to see reusing resources in a second. So let me remind you, I already present how you can do this commit and proof paradigm, where the proofer just commit the input and the output of each multiplication gates. Now our work is actually very centralized into a different way to view whatever you already see in this commit and proof paradigm. So let me show you now. So I'm going to show you a new way to do commit and proof. From the asymptotic point of view, there's no difference, but it's just a different view. So what do I mean here is that instead of we ask a proofer to commit the input of the circuit and the output of the multiplication gates, I'm going to ask the proofer to directly commit the input of the input of the circuit, output of multiplication gates, also whatever leave in the left wire, right wire, left wire, right wire of each multiplication gates. Okay, we just ask proofer to commit directly. So now let's think about, and we ask proofer to prove the arm-form multiplication correctly. Now let's consider this vector of commitment. What is this? So essentially here, L1 minus E1 show the difference between E1 and L1. I claim that in the honest execution, this must be 0. Right? Similarly, R1 minus E2 should be 0. And finally, this very right corner one, this O1 plus O2 plus E4 is nothing but just the output of the circuit should be also 0. So it means that this different way to prove zero-knowledge proof using commit and proof paradigm, well, what we do is just we show multiplication gate R-form correctly, and later on we show there's a vector which is the commitment of 0 vector. Okay, so let me say this more. Okay, yes, so let me say this more using some linear algebra. So what do I say here is that once you have this very large vector, which encoding the input and the output of each multiplication gate, also the left one and the right one of each multiplication gates. What the prover need to show to the verifier is just there's some public matrix. This matrix is defined just by the circuit. You give me a circuit, I know what the matrix look like. And what I need to show is that this matrix times this vector give you 0. Cool. Why? Okay, so why this is useful? It turns out that when we're targeting the branching, when we're targeting some disjunction statement, these multiplication vector can be reused across different branches. Okay, so what does it mean? So let me give you an overview of our Robin protocol, which stands for Refined Oblivious Branchings for Interactive Zero Knowledges. So here, imagine we just want to targeting this disjunction statement. They are all same size, there's two different circuits, but they have the same number of input and same number of multiplication gates. So now, instead of asking prover to prove left one and the right one twice, we can just ask a prover to commit the active, this vector belong to the active branch. Here, for example, if prover want to prove that the left one is correct, she can just commit the input left, right output for the left one, the witnesses for the left circuits. And also prover showing the multiplication gates are from correct. Now, if you think about what I'm going to show you, these two matrices already, or what I have shown you for these two matrices already, essentially here the prover just need to prove to the verifier that one out of these two matrices multiple this vector to 0. Say differently, this means that if you just take these two matrices, notice that these two matrices defined by the circuits already. I give two matrices, you will have two vectors of commitment, and one out of it is just 0. So I just reduce the problem to prove one of the circuit to prove that there is a 0 vector between two commitments. So how can you do it? Maybe you already see this trick before, but it's very simple. It suffices to the verifier to issue a random linear combinations, and it suffices for the prover to just show to the verifier that there's a random 0 is belong to the vector of t and with v1 and t with v2. Right? Because if there's a vector of all 0, no matter what the verifier going to issues, there always be 0 inside. If prover want to cheat, that means that v1 and the v2 are both not 0, then there's no way for the prover to show that 0 is belong to these two commitments as a single elements. Okay, so let me just show you some asymptotic analysis very quick. So for communications, here we need to commit this vector, this large vector. However, because I only committed on the active branch, so this is just order C, not order 2 times. It's not 2 times C. Okay, and similarly, so I skip the details here. You use volley-based proof. You can prove multiplication using just order 1 communications, but just believe me, you can do this. Okay, and finally, because when you take this matrix to calculate this V1 and V2, you only have linear operations, so this is free in communication. You have linear homomorphism. And essentially, finally, you just need to prove that this 0 is belong to these two commitment of element. What do? You just multiply it and show it's 0. Right, so this is just order B. So the entire communication is just order C plus B. Good, that means that let me emphasize that the reason why you can save this vector B here is because you only commit the vector on the active branch, not 2 branch.
I have a question.
Yes.
So in that last step, when you're showing that 0, that you have a bunch of commitments, one of which is 0, I mean, you said you do it in order B, which is the naive way, but there are techniques to do it in log B. Would that make your...
I think so. I think what you're going to show is something like you do some recursive combinations. The reason why you get log B is because you just compress this statement into half size, and you can have log B. Is that what you mean?
Yeah, there are a couple of different ways to do it.
Yes, yes. You can further improve it, but we did not consider this in this paper.
Okay.
Yeah, but essentially the crucial step here is that you reduce the problem for proving 0 vector belong to 2 vector to proving just a zero element belong two elements. That's a crucial step. You can further improve it, and we can discuss. I'm happy to discuss it after this talk. Okay, so let's continue. So what about the computation? So similarly, you need to commit this vector, this order C. You need to do some multiplication proofs. So believe me, it's order C. I'm not going to say why it is order C, but well, I haven't said how you can compute this M1 times this very large vector. This can be problematic because this may be some quadratic cost. Okay, so if you anyway, so but for the final step, to prove that zero is belong to these two elements, you only need order C to first compute this inner product, and you also order B to show zero is belong to these two elements. Okay, so this is where you have B times C. So this is where you have B times C here. But I still need to basically open how you compute this M times a large vector, because this can be the bottleneck in computations. So, and this is actually very problematic. This is because if you think about this matrix for a second, this part of matrix can be very sparse because the circuit can have unlimited fan out. So this part can be sparse. So if you just write out this matrix, save it in your local memory, and you do it naively, you just do multiplication, textbook multiplication, matrix multiplications, you will have quadratic in the circuit size. However, you don't have to do this. So to see why it is true, let's just now look at what exactly the semantic of this topology matrix. We call it topology matrix. Let's focus on this last row of the matrix. Okay, now I'm claiming that, for example, if you just targeting this one over here, these just show the contribution of O1 to the final output, right? Because this last column is used to define the final output. So the coefficients of this O1 is just show, okay, how many paths you can go from O1 to the outputs. Okay. Similarly, this one, very corner one here, is just show how O2 is contribute to the output. So essentially, what I do here, when I say M times P, what I really do is just evaluate the circuits. I just evaluate circuits forward. Right, so because if you take any P here, what you can imagine is what you're going to do is you just put value, you just put whatever inside this P vector at the correct place, and you evaluate circuits forward, and you just collect the value at the output place, and you will get the M times P. Okay, and a very similar, so that means that even though I use this matrix to present our work and to in this talk, this is just a concept. You never ever need to write it down in your memory when you implement it. You just evaluate circuits forward. That's it. So that's why your computation cost is just orders. And what's more cool is that you can not only evaluate M times P, you can also evaluate P times M. You put P on the left-hand side. So what does it mean? So you will take your it will take you a while to understand why this is true, but basically, when you times on the left-hand side, you just go from the output to the input. So I'm claiming that if you want to compute P times M, you just evaluate the circuits backward, not forward. So why I mention this, it seems that it is not useful in what I just present in these Robin protocols. You're going to see this is very crucial in our Batchman protocols. But just remember the fact that for arbitrary vector P, I can compute P times M in order C. Okay? So let's finish this Robin analysis because you only need order C per vector. So the total computation is just order B times C. Cool. So now remember what I said about reusing resources at the very beginning of this talk. The reason why you can achieve this Robin protocol is basically you reuse the multiplication tuples. You reuse the multiplication tuples on the active branch on the inactive branch. So to further improve Robin to get these Batchman protocols, what we really need is just reuse more resources. So for example, here I'm just going to show you what you can do, how you do Batchman protocols when you targeting this single destruction statement twice. Okay, meaning that you have this destruction statement, you want to do two proofs. The proof can can either use the same witnesses to 2 repetitions or use 2 different witnesses for 2 repetitions. It doesn't matter. So the first thing you can do is you just try to execute this Robin protocol twice. Let's see. You will see that the computation is not so good, but let's just see why it is not so good. Okay. So here, the fruitful can just commit the vector I mentioned on the first repetition, also the vector on the second repetitions. Okay, and according to our observations, it suffices for the proofer to show to the verifier that this V11 and V21, there's a 0 vector below these 2 commitment, and this V12 and V22, there's also a 0 vector below these 2 commitment. Let's just repeat it. Not so special. So essentially, what we can do is that we can require, again, we can still require the verifier to issue a random challenges, and we can reduce the problem to show that this single element 0 is belong to these 2 commitments. And this is for the first repetition on the left-hand side. And for the second, on the right-hand side, we have this second repetition, also shows 0 belong to these 2 commitments. That's it. However, if you think about the computation for a second, the proof and the verifier need to commit the order C on the first repetition, order C on the second repetition. It's order R times C. Okay, it's not grow with a factor B times R. The problem really is that here, per repetitions and per branch, I really need to compute M times this vector to get V11, and M2 times this vector to get V21, similar for the second repetition. So that's why this grow with the computation grow with a factor 4 in this specific example. So what we can do, our observation is actually very simple, is that we can reuse this T across these 2 repetitions. Instead of we just compute M times vector, we just ask a proofer to give me what is M times vector, and later prove that she gives the correct one. Okay, so for example, here, in these special examples, we can require the proofer to just give here A stands for the active one. If the proofer want to prove the first repetition, first branch, he just can compute T times MA1 and commit it. And similarly compute U2 as T times MA2 and commit it. And prove that these 2 inner product to 0. This already show that proof. This is of course not enough. Why? Because proofer can cheat. Proofer can commit arbitrary U. So we still need to ensure that U is a correct T times M1. We call this a topology vector because when you compute T times M1, you compress the matrix into a vector. But however, because T is reused across these 2 repetitions, so essentially what you need to show is just U1 and U2 both belong to a single set of vector where the size of the set is just big, because T is reused. Okay, so how can you do it? Let's reuse this random linear combination tricks one more time. What you can do is the verifier can issue a new random linear combinations, and the proofer just need to prove the verifier that there's 2 elements and belong to a vector, belong to a set of the value element where the set size is just order B. That's why we can also improve the computations. And let's just go through it very quick. What's asymptotic? So communications, similarly for both repetition, you need to commit order C. For the multiplications, oh sorry, this should be order 1. There's a typo here. It's both order 1. And finally, the proofer need to commit U1 and U2, which is again order C. And finally, you need to prove the inner product between these 2 elements equal to 0, which can be done in order 1. And finally, you need to prove that these 2 single elements belong to a public set of elements, which is order R times B. You can, by the way, you can optimize this part furthermore. But nevertheless, I will tell me that there's all the analysis you show, there's no term grow with like order R times B times C. Cool. So what about computation? Again, you need to commit the vector. You need to perform the multiplication gates per repetitions. The crucial step here is, because I reuse the same T, so both parties just need to calculate T times M1 and T times M2 to calculate this public set over here. Okay, and this is exactly where I need to introduce the trick, how you can compute an arbitrary vector P with N. That means that to compute T times NA1, you only need order C. To compute T times to compute T times M2, you also need order C. So it's order just 2C, not RBC. And essentially here, the proof also need to commit the U1, U2, you need order C. But nevertheless, finally, you just prove this each element belong to this C. This will be just order R times C. So the overall computation complexity is just order RB plus BC plus RC. Okay, so let me emphasize that the reason why you can do this is just you reuse this T times N1 and T times N2, and essentially you allow the proofer to commit it and prove it rather than just compute it. Cool. So let me just give you some concrete number when we evaluate this two scheme. So we implement this Batchman, we implement this robbing in this language, and instantiate this commit and prove zero knowledge using this for late-based zero knowledges. And this is how it speed up compared to the naive implementations where you just copy the circuit R times and B times and using some protocol called Quicksilver to perform it. And as you can see, this red line is just a speed up of this Batchman, and this blue kinds of line is a speed up robbing, and you just meet the asymptotic analysis. There's some myths I won't be able to cover in today's talk, but I want to mention it, is that the first one is that this Batchman protocol works better for large fields. You can check our paper to see why this is true. Also, you need to somehow design some mechanism to connect between two different repetitions. Otherwise, this proof is just trivial. If you can, it's not so surprised you can prove R repetition for a same statement multiple times. You need to somehow combine these two. For example, in the execution, the output of the first repetition is the input of the second repetition. You need to do it also for the paper for more evaluations. Okay, so with this, I want to go into the second half of today's talk. So remember, in this big picture where we want to build a ZK CPU, we need to tackle this question about ZK branchings, but we also need to tackle the questions how you can build a RAM machineries. This is the second topic. So now let's go into the RAM part. So what's the problem? What's the problem statement here is that we want to enable some kinds of gate inside the circuits, which allow you to do some access, right? You have memory. So this is very abstractly, but you have a memory wires, and you take an input, which is either read or write, and I stand for index, which slot you want to read or write, and the element X, either you put X inside the slot if it is a write. And essentially, you just want to achieve this semantic, meaning that you have an output of this access case, give you the memory access, memory I. You touch the index line, this is a readout. And if read and write equal to 0, meaning that it is a write, you also need to update this memory properly. Oh, sorry, the other way around. When read and write is 0, it means this is a read. When it is a write, you're going to basically update this memory. Okay, and let me set up some terminologies. So as you already see, kind of get the sense of in the prior first half of this talk, the linear gate is usually cheap. So in this work, we're just going to count the cost as how many non-linear gates we use, meaning how many multiplication gates we need to use and how many input gates we need to use. So just believe me, addition and scale gates. Scale means that you just take a scale to some constant, you multiply some constant. So this is cheap. So we are going to just focus on showing that you can do this very cheap in terms of using very small number of non-linear gates. And I'm going to use n to denote the size of the memory, for example, 2 to the power of 32. And I'm going to use t to denote how many times you're going to use this memory. Okay, and essentially what we show, again, I'm going to use this f to denote a large enough field. And this is not so surprising. I mean, from a feasibility point standpoint, okay? Because what you can do as a naive solutions is you just do linear scan, meaning that the verifier doesn't know which slot being accessed, but let's just try every single one and let's accumulate the result. Obviously, this is not so desirable, right? Because for each access, I need to touch every slot every time. It means that per access, I need to pay all the n costs or all the multiplications. And what we show in this paper is that when t is way larger than n, meaning that you have a RAM and you're going to access it many, many more times. And we only need, per access, we only need 4 inputs and 6 multiplication gates. So it's basically constant. And it's a very small constant, just 10. Okay, and in particular, I want to emphasize that this when I say T is way larger than N, it's just for simplicity. All you need is just T is omega N. Cool. So I want to say that actually we are not the first to do this constant overhead. There's some related work already achieved this constant overhead. So what we really achieve in this paper is that we achieve some concrete improvement in terms of number of gates. We have a smaller circuit. It's not about the implementations. It's about that we really have a smaller circuits where we have 20x improvement over this first paper on the left-hand side called constant overhead zero knowledge for RAM program. And we have a 3x improvement on this right-hand side, again, in terms of the circuit size, not real number, in terms of a circuit size. So with this, I want to discuss how we can achieve this. So as you already seen in the paper titles, we call our technique called two-shuffle make-a-ring. So what you're going to see is how you're going to use 2 permutation proof to achieve this RAM machinery, this read-write memory. And it's actually very simple and very cool. So essentially what you're going to see is I'm going to use 1 permutation to first build a memory that only allow you to read, not write. And finally, I'm going to show that by deploying another permutation and combine with this read-only memory, you can have a read-write memory. Okay, so let's go step by step and start with this permutation proof first. So what is let me say some preliminary. So let's start with this polynomial identity test. This means that the proofer and the proofer say, you can imagine there's one proofer come and say, here's 2 polynomial, and he want to prove to you that these 2 polynomial is the same. How can you do this? Is that the simple? It's like the verifier just issue a random challenges, and the proofer just prove to the verifier that these 2 polynomial evaluate as this random point R is equal. Okay. And essentially, this is called Schwarzschild lemma, if you're familiar with it. But this means that to prove the 2 polynomials is equal to each other, it's very simple. Just issue challenges and compute at this random point and show their equalities. And this can be extended into proof of the permutations. It means that if imagine the proofer just commit 2 vector x and a vector y, and the proofer want to show to the verifier that these 2 vectors just permute to each other. What you can do is essentially you just show that these 2 polynomial is the same polynomial, right? Because in some sense, this just means they have the same roots. Okay, and so how you can prove these 2 vectors permute to each other by using random challenges and evaluate these 2 polynomial, you just show that they evaluate to the same value. That's it. Very simple, and essentially, the crucial point here is that to prove the 2 vector permute to each other, I only need 2n minus 2 multiplication to basically calculate this product. And this can be generalized into some vector of tuples. It means that instead of defining this xi and the yi as an element, you can define xi and the yi as some fixed tuples. You need some extra trick, but you can this still preserve. Okay. So that means we can do permutation proof. For n element, we only need n multiplication tuple. So it's constant overhead. It's very small constant. It's 2n minus 2. Now I'm going to show you how you can use 1 permutation proof to build a so-called read-only memory. So remember in this read-only memory, what essentially you can imagine that here the proof and the verifier just agree on the state of the memory, meaning that the 0 should be x0, 1 should be x1. And later on, there's a circuit may just say that, okay, let's access unit I. Let's fetch whatever safe in the index I. The proofer know which is being fetched out, but verifier doesn't know I. Okay, so the key inside here is that as a proofer, proofer knows which unit need to be fetched out. So we can ask a proofer to just say, okay, this is the xi. But essentially, we need to preserve soundness. It means that we need to ensure that if the wire is holding value I, the proofer actually give me x1. Right? X says the wire hold the value 1, the proofer actually give me the x1. So our observation is very simple. We notice that we can achieve this by asking proofer to further give me two auxiliary value. One is called the one auxiliary value, which is the versions of the current read. So what do I mean? So imagine you have two array here. You have a two array which called reads and which called writes. And to initialize this array, I just first put 3 elements inside this write array. What I say here is just index 0, safe value x0, and the current version is 0. And we have index 1, x1, and the current version is 0. We have index 2, safe value x2, and the current version is 0. Okay, now let's assume that now we just want to read the index 1 elements. Essentially, we ask a proofer to commit the value, say this is the value, should be y0, and the current version is v0. So we're going to basically put a unit here. We say, Alice say, when we access the first unit, the result should be y0, and the latest version should be v0. And simultaneously, we write back to this write array with version +1. We basically consume the version 0 on this write array, and we create a new version v0 equal to 1 here. So similarly, you can do access for 0, and maybe the next one you also do the access for the index 1. And finally, we're going to ask the proofer to tell me what is the final versions per unit. Notice that this is zero knowledge. You commit the versions. The proofer doesn't say like how many times each unit is being accessed. But essentially, you can do this because the proofer can say the first unit save 0x0. The latest version is v3. Similarly, the proofer can say the index 1 safe value x1, and then the latest version is v4. Similarly, for this index 2 units. And the crucial observation is this. Is that it suffices for the proofer to just show to the verifier these two things commute to each other, right? What does this mean? This just means that, well, there's a, so let's focus on this, so for example, this index 1 access. To read the first time the proofer and the verifier want to read the index 1, you're going to put version 0, S0. And you're going to write back 1 versions over there. And you're going to, the second time you read this index 1, you're going to read the version equal to 1, these entries. And you're going to create a new entry, which is with version 2. And finally, you're going to cancel this version 2 out, which basically means that if these two things commute to each other, implies that this index 1 array also commute to each other. It suddenly means that all this v0, v2, all this y0, y1, and y2 should be all equal to x1. It means that you just achieve what's semantic for a radius. Okay, so let me show you a picture to further amplify the understanding. Here, this is just as time goes, and we have 3 values stored inside the read-only memory. So the first time you want to read the key one, I'm going to create a new version v1. I'm going to consume this v01, and I'm going to create a new one. And the second time when we access this index equal to 0 entries, we're going to create a new version v1 for this index 0 only. And similarly, the next time when we read this index 1, we just consume this v1 and create a new version called v2, which is used for the future read. And finally, we tear down it. We say that, okay, proofer, tell me what's the final version. You just cancel it out, cancel it, cancel out. It means that like basically it's commute to each other. So I want to emphasize this is very efficient because all you need is just the input, you input versions, and you do addition input. And finally, you do a permutation pull. You just 2 and -2 multiplications and some input to input this y0 and the v0 per access. So you might already notice that there's a very, very interesting attack. Maybe you think about it. Is that you don't really have to read from the past, right? As a cheating proofer, to make permutations for the first time I read the first unit, I can just read from the very last value. I can just read from the very last versions. This is attack, but this is just not an attack for the semantic of wrong. Because even though you read from the futures, as this is a wrong machinery, all you need to achieve is that every single read, the proofer gives the correct value x1. Even though you read from the future, it's still x1. So by saying this, I mean, you can imagine that you have this picture, even though you can read this V1 from where you tear down, but if it is the permutations, the value proofer claims stored in V0 in the index 1 are all the same, even though you read from the future. So it doesn't break any security. So let me see how many time left. 4. So now I'm going to showing you that. So basically, this finished how you can build a read-only memory. Now I'm going to show you that by having a read-only memory, you can also have a set membership check. This is actually very simple. I just showing you one slide. Essentially, the observation here is you can imagine you have a read-only memory where each element just saves nothing. Right? And then what is this? This basically is a set membership checker for the key entry. If the proofer wants to use something outside of this key, he should not be able to use it because you no way for the proofer to construct this permutation. You cannot cancel it out. And essentially, actually, even though in this example, in the read-only memory, you have a key space where it's 1, 2, 3, 4, 5. It's a continuously array. Here, you don't need to. You can have arbitrary sets. So I just going to name this as a zero-knowledge set, where the proofer and the verifier agree on some public known set. And each time the proofer just want to show to the verifier that some commitment is belong to this set. So if you think about it carefully, this is actually can be used in our Batchman protocols. Okay. Or finally, let me introduce the other permutation. So why we need the other permutation? So the reason why is exactly the attack I already described. The proofer can read from the futures. Okay, this will be very problematic if you think about that you also want to achieve writes. Because if you can read from the future in this read-write memory, the proofer can just forge whatever safe in this unit in the future and read from that unit he want to read. So besides to achieve a read-write memory, besides just doing this permutation proof, we also need to ensure that proofer can only read from the past, cannot read from in the futures. How can you do it? Well, it's very simple. You just maintain some global timestamp. And I'm going to claim that each time you just need to ask a proofer to say, what is the last time, what's the unit you want to read? When you, the unit we want to read, what is the last time you use it? And you just minus these two values and show that the difference is inside this set. Right? This basically means that this is a positive number, so you never read from the futures. So similarly, let me just go over it from a very quick examples. So let's say the first time the proofer want to read is the index 0 with value, like the proofer say the value is y0. And the time I'm going to read from is t0. Here, t0 should be equal to 0. That's where the unit is being created. And they just write back to this slot where it's 0, 6. Say this is a write, so you write back to 6. So 0, 6, 1. Why is the global time units? Okay, you just create a new slot that can be read and write in the futures with the current time span. And you need to prove that this 1 minus t0, which is just 1, is belong to this set. This means that proofer actually read from the past, not futures. Okay, so similarly, you can do the same thing. And finally, you just ask a proofer to give that, well, okay, finally, what's the last time you use it? And you just show they are permuted to each other. And with these kinds of set membership checkers, you ensure they read it from past. From this permutation proof, you show that they are formed correctly together. And there's two shuffle. Where's the two shuffle? The first shuffle is used to build this set membership checkers. And the second shuffle is just used to build whatever I present here, these two arrays are shuffled to each other. So that's it. That's how you build room. Very simple. And two shuffle makes array. And I just want to show you some concrete numbers where we implement this scheme and we actually compare to the paper I mentioned there, concrete number. We achieved some improvement according to our asymptotic analysis. So yes, with this, I guess it's a perfect time and I want to conclude. And this is where you can find our papers on ePrint, also our implementations if you are interested. And I'm happy to take any questions you have.
Thanks, the speaker. I think we do have time for one or two short questions. So
For the conjunction part, have you also looked at extensions of conjunction functions? Let's say that you have n circuits.
Yes.
And you want to prove in zero knowledge that maybe I of them hold, as opposed to proving that only one, that at least one of them. Have you also looked at this type
We
of
haven't think about this, but essentially, if you want to follow this paradigm, what you need to prove is that you have like several number of zeros. I think you can extend it naturally somehow, but we need to carefully think about it. Yes.
Okay. Thanks.
anyone else here? So for people joining online, you can also type the questions in the Q&A or raise your hand.
Yes.
I think we can grant your permission. Okay, if no question, I have one short question as well.
Yes.
So you talk about this disjunction proof, right? I can prove that I have an input which one of the circuit give me zero. But if you look at the C code we write a lot of branches, and it's not two program. It's one program but many branches in it. So how do you reconcile?
Yeah, so there's some misunderstood here. So I'm trying to say that you have a program and you have many basic blocks. Right? So each time you just execute one of these basic blocks.
Yes.
It's not like you have a disjunction and you have another disjunction, you have another disjunction inside the disjunction.
I see.
But overall, you can view it, the execution, as a disjunction over all basic blocks.
I see. Makes sense.
And you just repeat it. That's what I mean by repeating the disjunction multiple times.
Got it. Okay,
I've got
so
one if I could.
Yeah, feel free.
So just following up that question. So the circuit you're going to say is something like, I'm executing basic block number 7. I do these operations, and then the next basic block I will execute is number 15. Is that what the circuit would say for each basic block?
Yes and no. So the proofer is allowed to choose arbitrary block to execute, basically. But you still need to some actual mechanism to ensure that, for example, you have a PC register inside your program to indicate which basic block the proofer need to use. You can handle it, but in the scheme I just present, the proofer is allowed to select any basic block per repetitions.
Right. So the basic block itself needs to update the PC correctly to follow the program execution flow.
Yeah. For example, you can have inside the first basic block, you can have a constraint, say the first input minus 1 needs equal to 0. Now then the proofer can only use this basic block when the first input is 1.
Right.
Yes, that's what I mean. So you need some actual constraint to add it. But actually, in our ongoing research and the paper, we properly handle this very efficiently. But you can still handle it naively, meaning outside the disjunction statement.
Thanks.
Okay, if there's no more questions, let's thank the speaker again. And thanks you so much for joining the session today.